Got another question on the alcohols topic. So we're at number 3 now. So this covers the reactions of alcohols, and it also covers carbon-13 NMR. So if you haven't done NMR yet, you might want to miss out the second part of the question. As always, the link to the questions in the description of the video if you want to try it first, and I really hope you like the video. If you haven't already subscribed to the channel, why don't you think about doing that? Okay, so make a start. So I've highlighted the fact that this is an unsaturated alcohol, so it's obviously got a CC double bond, and just a reminder there that the sort of general formula for a saturated alcohol is CnH2n plus 1 OH. So the fact that this is an unsaturated alcohol means we have to take off 2 hydrogens, so the general formula is going to go to CnH2n minus 1 OH. So there's the balanced equation there. You could have just gone C6H12O there if you'd wanted to. It doesn't specify that you have to use molecular formula. I've gone for a top-heavy fraction there for the oxygens. You could have gone for 8.5 if you'd preferred. So moving on to part B, so you'll notice I've sort of highlighted the type of alcohol groups we've got in compound C, and we've got all 3 types. So we've got a secondary alcohol here, tertiary here, primary here, and the important thing to notice is this compound C is refluxed with the excess acidified potassium dichromate 6, which is obviously the oxidizing agent. So the secondary alcohol can be oxidized, it can only be oxidized to a ketone, so we're just going to get 1 oxidation there. Tertiary alcohols can't be oxidized. The primary alcohol, because it's reflux, can be oxidized twice to the carboxylic acid. So we're going to get a total of 3 oxidation reactions, so we need 3 moles of oxidizing agent. So there's the formula of the organic product, and I've missed the water out because I just want to quickly explain that you get 1 water produced in the oxidation of the secondary alcohol, and you only get 1 water produced in the oxidation of the primary alcohol, and that's when you form the aldehyde. You don't get a water produced in the second oxidation reaction, so we only need 2 moles of H2O. Okay, so moving on to part C, I've drawn up a sort of weird version of compound D just to show you where all the hydrogens are, because when alcohols are refluxed with sulfuric acid as a catalyst, you remove an H2O molecule. It's an elimination reaction and it generates an alkene. So what we need to think about is, obviously we've got to take the OH off to form water, but we also need to take off a hydrogen from an adjacent carbon atom, and there's quite a few adjacent carbon atoms to choose from. So the first structure I've drawn, you can see I've highlighted the atoms I've taken off. Obviously I've taken the OH groups off, but I've taken the hydrogen off this adjacent carbon here, and obviously that's generated a double bond there. And I've gone for this hydrogen here, which has put a double bond there. I could have gone for one of those, and obviously that would have put the double bond there, which would have been exactly the same molecule. So moving on to the second isomer, you'll notice I've left this alone, so we've still got this methyl group here. I've taken off this hydrogen, so I've got a double bond here now, and I've gone for that one there, so the double bond's there. And then the final one, I've done exactly the same thing on the left-hand side, so I've still got that there, but now I've gone for one of these hydrogens and put the double bond in that position there. So there's your 3 isomers there now. Moving on to the next part, so to convert an alcohol into an iodoalkane, essentially, you need a source of iodide ions, so you could either go for potassium iodide or sodium iodide, but you need to have sulfuric acid present as well. So I've gone for sodium iodide and sulfuric acid. Moving on to the last part, so there's your 4 structural isomers for that molecular formula that are all alcohols. So we've got butan 1-ol, butan 2-ol, 2-methyl-propan-1-ol and 2-methyl-propan-2-ol. So the first thing I want to do is look at how many different carbon environments we've got in each of these alcohols, and obviously that will indicate how many peaks you would get in the carbon-13 NMR spectrum. So you can see in butan 1-ol, all 4 carbon environments are different, so 4 environments for that one. Butan 2-ol, 4 environments again, so we're not going to be able to distinguish between those 2. 2-methylpropan 1-ol, we've got 3 carbon environments, so they're equivalent, and then we've got those 2 different environments there, so 3 for that one. And then for the 2-methylpropan 2-ol, you've got, they're all equivalent, so 1, 2 environments. So I'll just quickly read through my answer in case you can't decipher my scribble. So I'm saying unable to distinguish between butane 1-ol and butane 2-ol because they've both got 4 carbon environments. However, we can distinguish between 2-methylpropan 1-ol and 2-methylpropan 2-ol due to them having 3 and 2 carbon environments respectively.